On the night of December 19th, something passed our planet that did not belong to our solar system. There were no alarms, no warnings, no signs of danger. Just a faint point of light moving silently through space, too fast to stop and too distant to return. Most people never noticed it, but for astronomers, that night was a deadline, because this was not just another comet, it was a visitor from another star system. A natural object that had traveled through interstellar space for millions, possibly billions of years. Its name was 3I Atlas. And in the days surrounding its closest approach to Earth, scientists uncovered details that completely changed how we understand visitors from beyond our sun. This is not the basic story. This is what we learned when we finally got a close look.
And in the weeks around that flyby, the story of 3I Atlas changed, not because of conspiracy theories, but because of new measurements, new chemistry, new images from spacecraft that were never built to chase comets. This is not a basic "What is 3I Atlas" video. You already know that. This is the update, the part most summaries skip. The strange sun-facing tail, the wobbling jets, the molecules that hint at how chemistry works beyond our sun, and the worldwide search that asked a serious question and got a clear answer.
So let's start where the update begins, with the flyby that gave scientists their best chance before the universe took this object away again. 3I Atlas passed Earth at about 1.8 astronomical units, roughly 2 times the Earth-Sun distance. That's around 170 million miles, about 270 million kilometers. Far enough to be harmless, close enough to be worth an all-hands scientific response. Because interstellar comets are not just space rocks, they are samples, natural samples, made around another star in another protoplanetary disk under different conditions. If we can read them, we can compare them to what formed here. And that comparison is how science finds the big rules hiding behind the details.
The discovery story is already famous, but one detail matters for this update.
3I Atlas
Was first reported on July 1, 2025 by the NASA-funded Atlas Survey Telescope in Rio Hurtado, Chile. And within hours, astronomers realized the orbit was not closed, it was hyperbolic. That means the sun can't keep it. It came in from interstellar space, and it will leave to interstellar space. Then something else happened. Pre-discovery data turned up. Older images from other surveys traced it back to mid-June. And even more surprisingly, a scientific team later showed that NASA's TESS Space Telescope had been watching the same patch of sky much earlier, from May 7th to June 2nd, before anyone knew the visitor was there. Think about that for a second. An interstellar comet was already inside our data, already inside our cameras, and we didn't recognize it until it was almost too late.
Why is timing such a big deal? Because the most dramatic changes in a comet happen when it warms up. The closer it gets to the sun, the more ices sublimate. Gas and dust burst out, a coma forms, tails grow, jets appear, and those jets can act like tiny thrusters, altering the orbit in subtle ways. For 3I Atlas, the key dates looked like this. It reached its closest point to the sun around October 30th, 2025, about 1.4 astronomical units from the sun, just inside the orbit of Mars. After that, it moved into the glare of the sun from Earth's point of view. Ground telescopes lost it for a while. Then it re-emerged by early December, right on time for a final wave of observations, leading into the closest approach to Earth on December 19th. And while all of that was happening, scientists threw nearly everything we have at it.
First, Hubble. On July 21, 2025, Hubble took one of the sharpest images ever captured of 3I Atlas. It revealed a teardrop-shaped cocoon of dust around the nucleus, a visible sign that this object was active, behaving like a real comet, not a bare rock. Hubble also helped answer a question people kept arguing about: size. With comets, size is tricky because the nucleus is hidden inside a bright cloud of dust and gas. From Earth, you can easily mistake the coma for the nucleus. Hubble's measurements put an upper limit on the nucleus diameter, about 5.6 kilometers, but it could be much smaller, possibly only a few hundred meters across. That range sounds huge, and it is, but it's honest. It tells you what we truly know and what we still don't. Then came Webb. On August 6th, the James Webb Space Telescope observed 3I Atlas with its near-infrared spectrograph, and Webb did what it does best. It read light like a barcode. Early analysis, shared as a preprint, described a gas coma dominated by carbon dioxide, even when the comet was still about 3.3 astronomical units from the Sun. Webb's data included flux maps highlighting carbon dioxide near 4.3 microns and water near 2.7 microns, plus spectra that confirmed those signatures. Those observations showed molecular signatures consistent with carbon dioxide and water in the coma. In other words, this interstellar comet was carrying familiar volatiles, the same kinds of ingredients that drive comets in our own solar system. But here's what makes this important. Webb didn't just see a comet. It provided a way to compare the chemistry of an alien comet to the chemistry of local ones, with the sensitivity of a space telescope designed to study the early universe.
Now, the plot twist. Around perihelion, 3I Atlas became hard to see from Earth. But the solar system is not a single viewpoint. We have spacecraft all over the place, and one of them had the perfect angle: NASA's Parker Solar Probe. Parker was built to fly closer to the Sun than any spacecraft in history, to stare into the corona, to survive heat that would destroy ordinary missions. And in late 2025, Parker's Whisper camera observed 3I Atlas from October 18th to November 5th, about 10 images per day. To catch the comet, the spacecraft had to roll. The images were processed to remove the bright solar corona, and for scientists, this mattered for one simple reason. Parker watched 3I Atlas during a time when Earth basically couldn't. So while the comet vanished into sunlight for ground observers, Parker kept the story going. But the closest front row seat did not belong to Parker. It belonged to Mars. In early October, 3 NASA Mars missions got a rare opportunity. A comet from another solar system passed close enough to be seen from a planet that is not Earth. On October 2nd, the HiRISE camera on the Mars Reconnaissance Orbiter captured images of 3I Atlas. At the time, the comet was about 0.2 astronomical units from the spacecraft. That's roughly 18.6 million miles, about 29.9 million kilometers. In cosmic terms, that is close. HiRISE normally maps the surface of Mars. To image a comet, the orbiter had to rotate and point the camera at the sky. It's the same kind of unusual maneuver it used years earlier to observe another comet. The result was a tiny pixelated white ball, not the solid nucleus, but the coma, a cloud of dust and ice surrounding it. At the same time, MAVEN, another Mars orbiter, captured ultraviolet images. Over about 10 days starting September 27th, MAVEN observed the comet in multiple wavelengths and mapped hydrogen and hydroxyl in the coma. Why hydrogen? Because hydrogen is one of the most obvious fingerprints of water. When water molecules break apart under sunlight, they produce fragments, including hydroxyl, OH. So, by mapping those fragments, scientists can estimate how much water vapor the comet is releasing as it warms. And down on the surface, Perseverance joined in.
On October 4th, the rover used its Mastcam Z cameras to take long exposures of the night sky. Against a background of star trails, 3I Atlas appeared as a faint smudge, a robot on Mars watching a comet from another star. That is the kind of sentence that reminds you how fast astronomy is changing.
Now we reach the update that made headlines right after the Earth flyby. The tail that pointed the wrong way. Most people learn one simple rule. The comet's tail points away from the sun. Solar wind and sunlight push dust and gas outward. But in rare cases, comets can show an anti-tail, a feature that appears to point toward the sun. And 3I Atlas showed one. Not just an anti-tail, but structure inside it. New observations reported in late December described jet-like features in that sun-facing tail, and those jets were not steady. They moved. Researchers tracked the comet for 37 nights between July and September using the 2-meter twin telescope at Teide Observatory in Tenerife. They watched the jet structures shift in a repeating pattern, roughly every 7 hours and 45 minutes. From that wobble, scientists inferred something we desperately want for any interstellar visitor: rotation. The simplest interpretation is that the nucleus rotates about once every 15 hours and 30 minutes. This matters because rotation controls everything. Rotation controls which areas get sunlight, which areas heat up, where gas escapes, how jets form, and how the comet's brightness changes over time. In other words, the wobbling jets weren't just a cool visual, they were a direct clue to the comet's physics. And it's the first time we've measured this kind of behavior so clearly in an interstellar comet. In late November, a new ALMA study reported detections of methanol, CH3OH, in 3I Atlas. They also detected hydrogen cyanide, HCN. These molecules were mapped using the Atacama Large Millimeter and Submillimeter Array's compact configuration. The observations were taken on multiple dates: methanol on August 28th, September 18th and 22nd, and October 1st, hydrogen cyanide on September 12th and 15th. And here is what makes it fascinating. Methanol and hydrogen cyanide did not behave the same way. The study found that hydrogen cyanide production was depleted in the sunward hemisphere of the coma, but methanol was enhanced in that sunward direction. That implies different sources or different physical pathways. In the simplest picture, HCN looked consistent with direct release from the nucleus. Methanol may have had an additional source in the coma itself. And the ratio between methanol and HCN was striking, among the most enriched values measured in any comet at radio wavelengths. This is not proof of life. Let's be clear. Methanol and HCN are not living things, and comets are not biology. But these molecules matter for one reason. They are part of the chemical toolkit that can lead to more complex organics. So when an interstellar comet carries an unusually rich mixture of certain molecules, it tells us something big. It tells us that the chemistry we study in our solar system is not unique. The same kinds of ingredients can form elsewhere, and they can travel. Now, whenever a strange object appears, the public asks an uncomfortable question: could it be artificial? In the case of 3I Atlas, scientists did not ignore that question. They tested it. The Breakthrough Listen initiative coordinated Technosignature searches, looking for signs of artificial radio or optical emissions. They observed 3I Atlas with multiple facilities, from the Allen Telescope Array to the Green Bank Telescope. And the result was consistent across the searches. No technosignatures were detected. At the same time, some radio observations detected hydroxyl, OH, exactly what you expect when sunlight breaks down water molecules in a comet's coma, a normal, natural process. So the best, most sensitive tests did two things at once. They ruled out the exciting story that people wanted, and they strengthened the real story that science supports. 3I Atlas is a natural interstellar comet.
But even as a natural comet, it is still extraordinary, because its motion through the galaxy may carry a history. A July research paper analyzed the comet's kinematics, its speed and direction, and argued that 3I Atlas is likely older than the first two known interstellar objects, possibly several billion years old. The same work suggests it may have originated in a lower metallicity environment than earlier visitors. In simpler terms, it may come from an older generation of star systems. And if that's true, then 3I Atlas is not just from another star, it is from another era. Now comes the final question. What happens next? 3I Atlas is leaving. Its orbit is open. It will cross the solar system's outer regions and keep going into interstellar space. But it has one more notable encounter on the calendar. A trajectory study published in 2025 points to a close approach to Jupiter around March 16, 2026, at a distance of about 0.358 astronomical units. That's roughly 54 million kilometers. Not close enough to hit Jupiter, but close enough for gravity to matter. And close enough that scientists can ask a serious engineering question. Can any spacecraft near Jupiter get a better look? Some researchers have discussed the possibility of using the Juno spacecraft's presence at Jupiter to attempt an observation or even an intercept trajectory. Whether or not that ever happens, the fact that we can even ask the question tells you how far we've come. Because 3I Atlas is part of a new era. An era where interstellar objects are not myths or one-off miracles. They are becoming a category. Breakthrough Listen even notes optical observations involving the Vera C. Rubin Observatory. And as Rubin's sky surveys ramp up, discoveries like this may become more common, meaning the next interstellar visitor may not feel like a once-in-a-lifetime event. But 3I Atlas will always be special, because it arrived when we were ready. Ready with Hubble, ready with Webb, ready with radio telescopes, ready with spacecraft scattered across the solar system, ready to turn one faint, fast-moving point of light into a scientific story. A comet from another star system passed by, and the universe gave us a brief chance to learn. We did, and now it's leaving, carrying our curiosity behind it, into the dark between the stars.